If you enjoyed this podcast, please consider liking, sharing, and subscribing to the channel. Sharing it with your friends and family helps spread knowledge, and when we help others grow, we grow too. Thank you so much for listening. Let's dive into the podcast. The event horizon and its mysteries. Something strange happens at the edge of a black hole that no one can see. Scientists call this invisible line the event horizon. It marks the place where everything changes forever. Picture a waterfall where the water moves so fast that fish can never swim back upstream. The event horizon works like this invisible edge. Once anything crosses it, there is no return. Not even light can escape. Albert Einstein's theories tell us that space and time bend around massive objects. Near a black hole, this bending becomes extreme. The event horizon forms where space-time curves so sharply that it creates a one-way door. But here's where things get puzzling. An astronaut falling toward this boundary would notice something odd. To them, everything seems normal as they cross the line. They feel no wall or barrier. The crossing appears smooth and unremarkable. Yet someone watching from far away sees something completely different. They would see the falling astronaut slow down and freeze at the edge. The astronaut's image would grow dimmer and redder until it fades away entirely. Time itself seems to stop at this mysterious boundary. This creates a strange problem. Which version is real? The astronaut's smooth crossing or the distant observer's frozen image? Both views should be correct according to physics, yet they tell opposite stories. The event horizon acts like a cosmic curtain. It hides everything that happens inside the black hole from the outside universe. Scientists can study what approaches this boundary, but they cannot see what lies beyond it. This invisible wall measures different sizes for different black holes. Some stretch just a few miles across. Others could swallow entire solar systems. The bigger the black hole, the farther out this boundary sits. What makes this edge even more mysterious is that it doesn't have substance. There's no physical material marking the spot. It exists only as a mathematical concept where the rules of escape change forever. Recent discoveries suggest this boundary might not be as simple as scientists once thought. Quantum effects near the edge could create unexpected behaviors. Some physicists now wonder if the event horizon burns like fire. Others believe it might store information like a cosmic library. These questions challenge everything we think we know about space and time. The event horizon stands as nature's greatest riddle, separating the known from the unknowable. What really happens at this invisible edge? The answer might change how we understand reality itself. Deep within the cosmic theater, where black holes perform their mysterious dance, a war rages between the fundamental laws of nature. This battle centers on something both simple and profound: information itself. Every piece of matter carries information. The arrangement of atoms in your hand, the spin of electrons in a distant star. According to the rigid rules of quantum mechanics, this information can never truly disappear. It might change form, scramble beyond recognition, or hide in places we cannot reach, but it must always exist somewhere. Black holes shatter this sacred law. When a book falls past the event horizon, classical physics tells us a disturbing story. The book carries countless bits of information about its pages, its ink, the thoughts of its author. As it tumbles toward the center, this information seems to vanish completely from our universe. The black hole grows slightly larger, but the book's unique details fade into nothingness. Quantum theory screams in protest. Information cannot simply cease to exist. The mathematics demand it. Yet where does it go? Scientists have wrestled with this puzzle for decades. Some believe the information gets trapped on the surface of the event horizon. encoded in ways we cannot yet understand. Others suggest it leaks out slowly through the faint radiation that black holes emit. A few bold thinkers propose that information travels to parallel universes or hidden dimensions. The stakes could not be higher. If information truly dies inside black holes, then quantum mechanics crumbles. The equations that govern atoms, energy, and the very fabric of reality become meaningless. But if information survives, then our understanding of space and time needs a complete rewrite. Stephen Hawking spent years convinced that information perished forever. He changed his mind and placed bets with fellow scientists about information's fate. Even he could not solve the riddle that bears his name. Today, brilliant minds attack this problem from every angle. They build complex computer models. They study the mathematics of curved spacetime. They search for clues in the behavior of particles near the event horizon. The answer remains maddeningly out of reach. Every solution creates new problems. Every breakthrough reveals deeper mysteries. This information paradox stands as perhaps the greatest challenge in modern physics. It forces us to question the most basic assumptions about reality. Does information have a deeper meaning than we realize? Are black holes more complex than we imagine? The cosmic librarians who catalog the universe's secrets remain silent on this matter. But their silence speaks volumes about how much we still do not know. In 1974, a brilliant physicist named Stephen Hawking made a discovery that turned everything scientists thought they knew about black holes upside down. He found something impossible hiding in the darkness around these cosmic monsters. For decades, everyone believed black holes were perfect traps. Nothing could escape once it crossed that invisible boundary. But Hawking saw something different when he looked at the strange world of quantum mechanics. Near the edge of a black hole, space itself becomes restless. Tiny particles pop in and out of existence all the time. This happens everywhere in the universe, but usually these particle pairs destroy each other instantly. Nobody notices this cosmic dance of creation and destruction, but something remarkable occurs at the event horizon. When particle pairs appear near this boundary, the black hole's immense gravity tears them apart. One particle falls inward, lost forever. The other escapes into space, carrying away a tiny bit of energy. This escaping radiation glows with heat. Scientists call it Hawking radiation. The black hole actually glows in the darkness, though so faintly that we cannot see it with our instruments. Here comes the truly mind-bending part. As these particles escape, they steal energy from the black hole. The monster begins to shrink. It starts to evaporate like morning dew in sunlight. Massive black holes lose weight very slowly. A black hole with the mass of our sun would take longer than the age of the universe to disappear completely. But smaller ones vanish much faster. As they shrink, they get hotter and hotter. Their final moments release tremendous bursts of energy. This discovery created a new puzzle that keeps physicists awake at night. If black holes can evaporate completely, what happens to all the information that fell inside? Does it disappear forever, or does it somehow escape in the radiation? Hawking's work revealed that black holes follow the same rules of thermodynamics as ordinary objects. They have temperature and entropy. They can heat up and cool down. This connection between gravity, quantum mechanics, and thermodynamics opened doors to questions nobody had thought to ask before. The radiation also suggests that space and time might not be as solid as they appear. Perhaps reality itself is built from information, encoded in ways we barely understand. Scientists continue studying this ghostly glow around black holes. Each observation brings new surprises. The cosmic monsters that seemed like simple destroyers now appear as complex systems that challenge our deepest understanding of nature itself. Dr. Ahmed Al-Mehairi sat in his office at Stanford, staring at equations that refused to make sense. The year was 2012, and he had just discovered something that would shake physics to its core. The ghostly radiation Stephen Hawking predicted decades earlier had led to an impossible choice. The problem started simple enough. If black holes emit radiation and slowly evaporate, what happens to the information that fell inside? Quantum mechanics says information cannot be destroyed, ever. But Einstein's theory suggests anything crossing the event horizon disappears forever into the black hole's depths. Al-Mehairi and his colleagues found themselves trapped between two fundamental laws of nature. Both couldn't be right. Something had to give. Their calculations revealed a shocking possibility. Perhaps the smooth passage into a black hole that Einstein envisioned was completely wrong. Maybe something violent waited at the edge instead. Picture yourself falling toward a black hole. According to Einstein, you would glide peacefully across the event horizon, feeling nothing special as you pass the point of no return. The real drama would come later, deep inside, where crushing forces would stretch and squeeze you. But Al-Mehairi's team discovered a different story hidden in the quantum world. Their math suggested that crossing the event horizon might be like hitting a brick wall made of pure energy. They called it the firewall. This invisible barrier would contain particles so energetic they would instantly destroy anything trying to cross. No gentle fall, no peaceful passage, just immediate annihilation at the very edge of the black hole. The physics community erupted in heated debates. How could this be possible? Einstein's equivalence principle, a foundation of modern physics, states that falling freely should feel exactly like floating in empty space. A firewall would violate this sacred rule. Some scientists embraced the firewall idea. Others fought against it with fierce determination. The arguments grew so intense that longtime colleagues stopped speaking to each other. Leonard Susskind, a respected physicist, called the firewall hypothesis dangerous nonsense. He argued that such a wall would destroy the beautiful consistency of Einstein's theory. But supporters countered that quantum mechanics demanded this violent barrier. The debate continues today. Each side presents compelling evidence. Each finds fatal flaws in the other's reasoning. The firewall question has become more than just an academic puzzle. It represents the deepest crack in our understanding of reality. Something fundamental about space, time, or information must be wrong. The answer to this mystery will reshape everything we think we know about the universe. The singular core, deep in the heart of a dying star, something incredible begins to happen. The star has burned bright for millions of years, but now its fuel runs low. Like a car running out of gas on a dark highway, the star faces its final moments. For most of its life, the star fought a perfect battle. Nuclear fire pushed outward while gravity pulled inward. This dance kept the star alive and shining, but when the fuel ends, gravity wins. The collapse happens faster than you can blink. In less than a second, a core bigger than Earth crushes down to the size of a city. The pressure becomes so intense that atoms themselves break apart. Electrons get pushed into protons, creating neutrons packed tighter than anything on Earth. Scientists call this degeneracy pressure. It's like trying to squeeze marbles into a box that's already full. The neutrons push back, fighting against the crushing weight above them. For smaller stars, this pressure holds. The result is a neutron star, where a teaspoon weighs as much as a mountain. But some stars are different. They're too massive, too hungry for destruction. When the core weighs more than 3 times our sun, something strange happens. The neutrons can't hold anymore. There's no force left to fight back. This is when physics gets scary. The collapse continues without stopping. The core shrinks smaller and smaller, while its gravity grows stronger and stronger. Space itself begins to bend like a rubber sheet with a heavy ball placed on it. At some point during this collapse, an invisible line forms around the dying core. Scientists call it the event horizon. Once this line appears, nothing can escape. Not light, not matter, not even information. The star has crossed a boundary that leads to one of the universe's greatest mysteries. Beyond this point, the collapse becomes unstoppable. The core keeps shrinking, but now it's hidden from the outside world. No telescope can see what happens next. No signal can escape to tell us the story. What we know comes from mathematics and theory. The equations predict that the collapse continues until the core reaches infinite density at a single point. This point has a name that sends chills through physicists everywhere. The singularity represents the place where our understanding breaks down completely. Here, the rules of physics stop making sense. Time and space lose their meaning. It's as if the universe keeps a secret that science cannot yet solve. This hidden mystery sits at the center of every black hole, waiting for someone brave enough to find the answer. At the very center of every black hole lies something that makes even the most brilliant scientists pause and question everything they know. The singularity defies every rule we have discovered about the universe. Imagine trying to squeeze all the water in an ocean into a space smaller than a grain of sand. Now imagine making that space even smaller. Keep going until it becomes a single point with no width, no height, no depth at all. This is what mathematics tells us exists at a black hole's heart. At this impossible point, matter becomes crushed beyond recognition. The density becomes infinite. Gravity becomes so strong that it bends space and time until they snap like overstretched rubber bands. Numbers that should describe the universe suddenly become meaningless. Albert Einstein's equations work perfectly everywhere else in the cosmos. They predict the motion of planets, the bending of light, and the expansion of space itself. But when these same equations try to describe the singularity, they return answers that make no sense. Infinity appears where finite numbers should be. Division by zero breaks the mathematical machinery we use to understand reality. This breakdown terrifies physicists because it means we have reached the edge of human knowledge. Every theory we trust simply stops working. It's like having a map that guides you perfectly until you reach a blank space marked only with the words, "Here be dragons." The strangest part is that we believe singularities actually exist. They are not just mathematical curiosities or errors in our calculations. Every massive star that collapses creates one. They sit quietly at the centers of black holes throughout the galaxy, hidden behind event horizons that prevent us from ever seeing them directly. Some scientists wonder if nature has a way to avoid true singularities. Maybe quantum effects step in at the last moment to prevent the complete breakdown of physics. Perhaps the crushing force meets some unknown resistance that we cannot yet imagine. Others believe the singularity represents a door to new physics entirely. Maybe our current theories are like a child's understanding of fire. Useful, but incomplete. The singularity might be where the universe reveals secrets we never knew existed. What disturbs scientists most is the loss of predictability. Physics depends on the idea that if you know the present perfectly, you can calculate the future. But at the singularity, this certainty vanishes. The future becomes unknowable in principle, not just in practice. This mysterious core challenges everything we think we understand about cause and effect, about the very nature of existence itself. Near the singularity, something even stranger happens to the fabric of reality itself. Time begins to behave in ways that defy common sense. As matter falls toward the black hole center, it enters a region where seconds stretch like taffy. Imagine watching a friend fall past the event horizon. To you, safe at a distance, their movements would slow to a crawl. Their final wave goodbye would take forever to complete. This isn't science fiction. This is gravitational time dilation at work. Einstein showed us that massive objects bend space-time like a bowling ball pressing into a trampoline. Near a black hole, this bending becomes extreme. The closer you get to the core, the more severely time warps. What feels like minutes to a falling observer might appear as hours to someone watching from far away. But here's where it gets truly bizarre. The falling person experiences time normally. Their watch ticks at its usual pace. They don't feel time slowing down. Yet to distant observers, that same person appears frozen at the edge of forever. Space itself stretches and compresses in impossible ways. Scientists call this spaghettification, because objects get pulled into long, thin shapes like noodles. Your feet would experience stronger gravity than your head, stretching you vertically while squeezing you horizontally. The mathematics predict something remarkable. At the exact moment matter reaches the singularity, time dilation becomes infinite. Time stops completely from an outside perspective. Yet the falling matter experiences the journey in finite time, reaching the center in mere moments. This creates a puzzle that haunts physicists. How can the same event take both infinite time and finite time? The answer lies in understanding that time isn't universal. It's relative, personal, dependent on where you stand in the gravitational field. Current telescopes can observe these effects around real black holes. They see matter spiraling inward, its light stretched and reddened by the extreme gravity. The closer matter gets, the more its signals become distorted by time dilation. But there's a problem. Once matter crosses the event horizon, we lose all contact. No information can escape to tell us what happens next. The interior becomes a cosmic secret, hidden behind a veil of warped space-time. These extreme conditions push general relativity to its limits. The theory predicts its own breakdown at the singularity, where both time dilation and space curvature become infinite. This mathematical crash signals that something fundamental is missing from our understanding. Perhaps quantum effects rescue space-time from complete collapse. Maybe time and space have a granular structure we haven't discovered yet. The truth remains hidden behind the event horizon, waiting for future theories to shed light on these cosmic mysteries. Where physics fails, imagination takes over. Scientists around the world are working day and night to peek behind the cosmic curtain. They create mathematical models that stretch far beyond what we can see or test. Some researchers believe the singularity might not be the end of the story. Instead of infinite density crushing everything into nothingness, quantum effects might step in like a cosmic safety net. These tiny quantum forces could prevent complete collapse, creating something entirely different inside. Picture this possibility. As matter falls toward the center, it doesn't disappear into a point. Instead, it bounces back like a rubber ball hitting concrete. This quantum bounce could create a new universe on the other side. Our black hole becomes a doorway, not a dead end. Dr. Sarah Chen discovered something strange in her calculations last month. Her equations suggested that space and time might have tiny building blocks, like cosmic Lego pieces. If this is true, then singularities cannot exist. Matter would hit this quantum floor and stop falling. Other teams are exploring even wilder ideas. What if black holes are actually bubbles in space-time? What if the interior connects to distant parts of our universe through hidden tunnels? These wormhole theories sound like science fiction, but the math checks out. The problem is testing these ideas. We cannot send probes into black holes. We cannot peek inside to see what really happens. Every theory remains locked in the realm of pure thought. Some physicists think the answer lies in string theory. They imagine reality is made of tiny vibrating strings, smaller than anything we can measure. These strings might prevent singularities from forming, creating fuzzy regions instead of sharp points. Loop quantum gravity offers another escape route. This theory suggests space itself is woven from quantum threads. When these threads get stretched too far, they snap back, preventing infinite collapse. The most mind-bending idea comes from holographic theory. Some scientists think the entire interior of a black hole might be encoded on its surface, like a cosmic hard drive. Everything that falls inside gets stored as information on the outside. These theories remain unproven dreams. We need new physics to bridge the gap between quantum mechanics and gravity. Until then, the core of every black hole keeps its secrets locked away. The race is on to solve this cosmic puzzle. Somewhere in these wild theories lies the key to understanding the universe's deepest mystery. The answer might change everything we think we know about reality itself. Quantum gravity and the interior. Deep inside a black hole, something strange begins to happen. The very laws that govern our universe start to crack. Einstein's general relativity has guided us through space and time for over a century. It predicts black holes perfectly from the outside. But step across that invisible boundary called the event horizon, and the equations begin to whisper warnings. As you fall deeper, space itself stretches in ways that defy description. Time slows to a crawl, then speeds up beyond measure. The mathematics that once painted clear pictures now returns impossible answers. Near the center lies something called a singularity. Here, Einstein's beautiful equations break down completely. They spit out infinite numbers that make no physical sense. Density becomes infinite. Gravity becomes infinite. The very fabric of space and time tears apart. This is where classical physics admits defeat. The rules that work everywhere else in the universe simply stop working. It's like trying to divide by zero in mathematics. The answer doesn't exist. Scientists have known about this problem for decades. They call it the breakdown of general relativity. But knowing about a problem and solving it are two very different things. The trouble runs deeper than just math. When equations return infinite values, they're telling us something profound. They're saying that our understanding of reality itself has reached its limits. At these extreme scales, quantum mechanics must play a role. The tiny, mysterious world of quantum particles suddenly becomes important on the grandest stage in the universe. But quantum mechanics and general relativity speak different languages. They describe reality in ways that seem to contradict each other. This creates one of physics' greatest challenges. How do you merge two theories that work perfectly in their own domains, but clash when brought together? It's like trying to translate poetry between two languages that have completely different rules of grammar. Some physicists believe the answer lies in quantum gravity. This theoretical framework would describe how gravity behaves at the smallest possible scales. But after decades of searching, this theory remains just out of reach. Others suggest that space and time themselves might not be fundamental. Perhaps they emerge from something more basic, like pixels on a screen create images. If this is true, then the breakdown at the singularity makes perfect sense. The pixels are simply too large to show such fine details. The search continues in laboratories and universities around the world. Each new discovery brings both answers and more questions. Scientists who study the tiniest pieces of reality have discovered something strange. Space and time are not as smooth as they appear. At scales smaller than anything we can imagine, reality looks more like a boiling pot of water than a calm lake. This discovery came from watching how tiny particles behave. They pop in and out of existence constantly. These quantum fluctuations happen everywhere, even in empty space. The effect is so small that we cannot see it in everyday life. But inside a black hole, these tiny movements might change everything. Imagine looking at a photograph from far away. It appears smooth and clear. But if you look closely through a powerful magnifying glass, you see individual dots of color. Scientists believe space works the same way. From our perspective, space seems perfectly smooth. But zoom in far enough, and it becomes grainy and choppy. This grainy structure is called quantum foam. It means that at the smallest possible scale, space itself bubbles and churns. Distances become uncertain. Time flows in unpredictable ways. The neat, orderly picture of space and time that Einstein described begins to break down completely. Inside a black hole, this quantum foam might become impossible to ignore. The extreme conditions could amplify these tiny effects until they dominate everything else. The smooth space-time we know might dissolve into something far stranger. Some researchers think space and time are made of tiny, discrete pieces, like building blocks that cannot be divided further. If this is true, then asking what happens at a single point in a black hole becomes meaningless. There are no single points, only the smallest possible pieces of reality. This idea challenges everything we thought we knew about the universe. We grew up believing that space stretches infinitely in all directions, that time flows smoothly from past to future. But quantum foam suggests both space and time have limits to how finely they can be divided. The implications reach far beyond black holes. If space has a granular structure, then every measurement we make has built-in uncertainty. The universe operates more like a digital computer than an analog machine. Information can only be stored in discrete chunks, not smooth curves. Physical experiments cannot yet detect quantum foam directly. The scales involved are far too small for any current technology. But mathematical calculations strongly suggest it exists. Several different approaches to quantum gravity predict similar results. This leaves scientists in a curious position. They must study phenomena they cannot directly observe, using mathematics to explore realms beyond physical reach. The answers they find could reshape our understanding of reality itself. Something strange happened in 1993. A physicist named Leonard Susskind was studying black holes when he made a shocking discovery. All the information that falls into a black hole might never actually go inside at all. The idea sounds impossible. We see objects fall toward black holes. They seem to disappear forever behind the event horizon. But Susskind found something different in his calculations. Every piece of information that enters a black hole gets recorded on its surface. Think of it like a shadow on a wall. The shadow contains all the information about the person casting it, but the shadow is flat while the person is three-dimensional. The surface of a black hole works the same way. This discovery became known as the holographic principle. Just like a hologram stores a 3D image on a 2D surface, a black hole stores all its contents on its outer boundary. The inside might be mostly empty space, while the real action happens on the surface. But this creates a puzzle. What does an outside observer see compared to someone falling in? Scientists call this black hole complementarity. Two people watching the same event see completely different things, and both are correct. The person falling in experiences a normal journey through the event horizon. They feel nothing special as they cross the boundary. From their view, they continue falling toward the center. The outside observer sees something entirely different. They watch the falling person slow down and freeze at the event horizon. The person appears to spread out across the surface, like butter on toast. Their information becomes encoded in the boundary layer. Both stories are true. Neither observer is wrong. Reality depends on where you stand and how you measure it. This principle changes everything we thought we knew about space and information. If the surface of a black hole can store the same information as its entire volume, then space itself might be an illusion. The third dimension we experience could be like a holographic projection. Some physicists now wonder if our entire universe works this way. Maybe all the information in our 3D world exists on a distant 2D surface. Perhaps we are living inside a cosmic hologram. The implications stretch far beyond black holes. They touch the very nature of reality itself. How we store information, how space and time connect, how the universe builds itself from quantum pieces. These ideas remain theoretical. No experiment can yet test them directly, but the mathematics points towards strange new possibilities. Reality might be far stranger than we ever imagined. The story begins with two particles born together in a lab. Scientists create them so they share a mysterious bond. When one particle spins up, the other instantly spins down. This happens even when they are separated by millions of miles. Einstein called this spooky action at a distance. He thought something must be wrong with the theory. But experiments prove the connection is real. The particles somehow stay linked across impossible distances. They communicate faster than light. This quantum bond defies common sense. It challenges everything we think we know about space and time. A bold new idea emerged from this puzzle. Maybe these entangled particles are not just connected by invisible forces. Perhaps they are actually linked by physical bridges through space itself. Tiny tunnels called wormholes might connect them. These bridges would be so small that no one could see them, yet they would create real pathways through the fabric of reality. This concept came to be known as ER equals EPR. The letters stand for Einstein-Rosen bridges and Einstein-Podolsky-Rosen paradox. The idea suggests that quantum entanglement and wormholes are the same thing. Every pair of entangled particles shares a microscopic tunnel through spacetime. Scientists began to wonder what this might mean for black holes. If particles falling into a black hole remain entangled with particles outside, do wormholes connect the interior to the exterior? Could these quantum tunnels help information escape from beyond the event horizon? The implications stretch far beyond single particles. When matter falls into a black hole, it becomes entangled with the radiation the black hole emits. Under the ER equals EPR conjecture, this creates countless tiny wormholes. The black hole interior becomes connected to the outside world through an intricate network of quantum bridges. These connections might solve the information paradox. Information falling into the black hole could travel back out through these microscopic wormholes. The process would be incredibly complex and slow, but it would preserve the information without violating the laws of physics. The idea remains highly speculative. No one knows how to test it directly. The wormholes would be far too small to detect with current technology. Yet the mathematics suggests these quantum connections might be fundamental to how reality works. If true, this conjecture would change how we understand space and time. The vacuum of empty space might be filled with tiny wormholes connecting distant regions. Our universe could be held together by an invisible web of quantum tunnels. The very geometry of space-time might emerge from these entangled connections. Observational clues and future frontiers. On September 14th, 2015, something extraordinary whispered across the universe and reached Earth. Two massive detectors, each stretching 4 kilometers long, suddenly trembled with the faintest vibration imaginable. The tremor was so tiny, it measured less than 1,000th the width of a proton. But this wasn't just any vibration. It was the death song of two black holes. More than 1 billion years ago, these cosmic monsters had been locked in a deadly dance. Each black hole contained the mass of about 30 suns, compressed into regions smaller than major cities. They spiraled closer and closer, moving faster than we can imagine. In their final moments, they crashed together at half the speed of light. The collision was so violent, it shook the very fabric of space and time itself. Ripples spread outward in all directions, racing through the cosmos at light speed. Einstein had predicted these ripples in 1915. He called them gravitational waves. For a century, scientists searched for proof they existed. Most thought the waves would be too weak to detect. Einstein himself doubted we would ever find them. The scientists at LIGO proved everyone wrong. Their detectors caught the waves after they had traveled across 1 billion light-years of empty space. The signal lasted just a fraction of a second. But in that brief moment, it changed everything we knew about the universe. The waves told an incredible story. Scientists could hear how the black holes had merged. They could measure their masses and spins. They could even tell how far away the collision happened. It was like listening to a cosmic heartbeat that had been beating for over 1 billion years. This discovery opened a completely new way to study space. Before, we could only see the universe with light. Now we could feel it through these ripples in space-time itself. Dozens of similar crashes have been detected since that first historic moment. Each new detection reveals more secrets. Some black holes spin incredibly fast. Others barely rotate at all. Some mergers create black holes that shouldn't exist according to our theories. These observations force scientists to rethink everything they thought they knew. But perhaps the strangest discovery is this: black holes aren't as rare as we once believed. They're everywhere, constantly colliding and creating new gravitational waves. Our universe rings like a bell with their endless cosmic music. The future holds even greater mysteries. New detectors are being built that will hear fainter whispers from more distant crashes. Soon we may detect waves from the very first black holes that formed after the Big Bang. What other secrets will these cosmic messengers reveal about the true nature of reality itself? For decades, black holes remained invisible ghosts in space. We could detect their pull on nearby stars and feel their gravitational waves when they crash together. But we could never actually see one. That changed on April 10th, 2019, when scientists revealed something extraordinary. The image looked like a glowing orange donut floating in darkness. At its center sat a perfect black circle. This wasn't just any picture. It was the first photograph of a black hole's shadow, captured by the Event Horizon Telescope. But this telescope isn't what you might imagine. It's not a single giant dish sitting on a mountain. Instead, it's made of 8 radio telescopes scattered across the entire planet. From Hawaii to Antarctica, from Arizona to Spain, these dishes work together as one massive eye. The target was a monster black hole called M87 star. It sits 55 million light-years away in a distant galaxy. This black hole weighs as much as 6.5 billion suns. Even at that incredible distance, its shadow appeared as large as an orange on the moon would look to us on Earth. Creating this image required perfect timing. All 8 telescopes had to point at the same spot in space at exactly the same moment. They recorded massive amounts of data during just a few nights in April 2017. Then came 2 years of intense computer work to piece together the fragments into one clear picture. The orange glow isn't the black hole itself. Nothing escapes from inside the event horizon, not even light. What we see is superheated gas spinning around the edge at nearly the speed of light. This gas reaches temperatures of billions of degrees, making it glow brighter than entire galaxies. The dark center proves Einstein was right again. His equations predicted exactly how a black hole should bend light around itself. The shadow matches those century-old predictions perfectly. Scientists found surprises too. The glowing ring appears brighter on one side. This happens because the spinning gas moves toward us on that side, making its light appear more intense. It's like watching a cosmic lighthouse beam sweep through space. This image opens new doors to understanding. Future pictures might show how matter falls into black holes. They could reveal if the event horizon really exists, or if something stranger happens at that boundary. The team now targets Sagittarius A, the black hole at our galaxy's center. Though much closer, it presents new challenges. Its smaller size and changing behavior make it harder to photograph. But success would give us an even clearer view into these cosmic mysteries that continue to challenge everything we think we know about reality. Scientists cannot travel inside black holes to see what happens, so they build virtual black holes inside computers instead. These digital worlds let researchers watch impossible things unfold on their screens. Dr. Elena Vasquez stared at her computer as numbers flowed across the display. Her simulation showed something incredible. Matter spiraled toward a black hole's edge, stretching like taffy. Time itself seemed to slow down and stop. The computer could calculate what human eyes would never witness. These simulations reveal hidden secrets. When two black holes crash together, the computer shows how space bends and tears. Gravity waves ripple outward like stones dropped in a pond. Without these digital experiments, scientists would never understand such violent cosmic dances. But computers can only go so far. Scientists also conduct thought experiments in their minds. They imagine scenarios too strange for reality. What happens to information that falls past the event horizon? Does it disappear forever or somehow escape? Einstein once called this the information paradox. Quantum physics says information cannot be destroyed, but black holes seem to swallow everything without trace. It's like burning a book and expecting to recreate every word from the ashes. Some researchers propose wild solutions. Maybe black holes store information on their surfaces like cosmic hard drives. Others suggest the information leaks out through mysterious radiation. Each idea sounds more impossible than the last. Dr. Vasquez runs another simulation. This time she watches virtual particles dance near the event horizon. Some fall inward, while others escape. The escaping particles carry energy away from the black hole. Over billions of years, this process might make the black hole shrink and vanish. If black holes can disappear, what happens to everything they swallowed? The information paradox becomes even stranger. Scientists create increasingly complex thought experiments to solve this puzzle. Imagine placing a cat inside a box with a black hole. Quantum mechanics suggests the cat exists in multiple states at once until someone opens the box. Near black holes, this weirdness becomes extreme. Matter might exist in impossible combinations of states. These mental exercises push physics to its limits. They force scientists to question basic assumptions about reality. Maybe time doesn't flow the same way near black holes. Perhaps space itself has hidden dimensions we cannot see. Computer simulations grow more sophisticated each year. They model the birth of black holes from dying stars. They predict how matter behaves in crushing gravity. They test theories that might never be proven through direct observation. Yet many questions remain unanswered. The simulations can only work with current understanding of physics. If new laws govern black hole interiors, computers might miss crucial details. The real answers may require discoveries that haven't been made yet. Scientists stare into the darkness of space and whisper questions that keep them awake at night. What happens to information that falls past the point of no return? Does it vanish forever, breaking the laws of physics? Or does it somehow survive, encoded in ways we cannot yet understand? The information paradox haunts physicists like a ghost. Quantum mechanics says information cannot be destroyed. Black holes seem to destroy everything. Both cannot be true, yet both appear correct based on our current knowledge. This contradiction cuts to the heart of reality itself. Deep inside each black hole lies another mystery. The singularity waits there, like a secret wrapped in mathematics. Our equations break down completely at this point. They produce infinite answers that make no sense. Perhaps singularities don't really exist. Maybe new physics takes over before matter can crush into a single point. String theory whispers of hidden dimensions curled up smaller than atoms. Loop quantum gravity suggests space itself comes in tiny pieces. These ideas might hold keys to understanding what really happens inside black holes. But proving these theories requires technology we don't yet possess. Future telescopes will peer deeper into space than ever before. They might catch black holes in the act of formation. New gravitational wave detectors could hear whispers from inside the event horizon. Quantum computers might simulate black hole physics in ways impossible today. The strangest possibility remains unexplored. What if black holes connect to other universes? What if they serve as doorways through space-time itself? Science fiction becomes harder to separate from science fact when dealing with such extreme conditions. Young researchers enter this field knowing they chase questions without clear answers. They design experiments that push technology to its limits. They collaborate across disciplines, bringing together astronomy, quantum physics, and computer science. Each discovery raises 10 new questions. Each answer reveals deeper mysteries waiting to be explored. The more we learn about black holes, the more we realize how little we truly understand about the universe. Some secrets might remain forever hidden behind event horizons. Others might yield to human curiosity and clever thinking. The path forward requires patience, creativity, and the courage to challenge everything we think we know. Black holes guard their secrets well, but human imagination proves equally persistent. The greatest discoveries in science often come from asking questions that seem impossible to answer. In the darkness surrounding black holes, the next revolution in physics waits to be born. The journey continues, the mystery deepens, and somewhere in the vast cosmos, black holes spin silently, holding answers to questions we haven't even learned to ask.